Hello AP Chemistry and welcome to our demo and discussion on galvanic cells. So clearly this is not going to be as fun as our normal demo and discussion, but we will do our best. So like it's going to say, like every once in a while I will tell you to pause, so pause and think about the question on your own, right, just like you would during class, because that's where it happens, right? That's where you get the chance to think about it. And then we'll talk about it together and we'll just go back and forth, right? Kind of like we do in class as best we can. Big thing, right? So obviously this is the perfect chapter to end with. Like it says on Power School, this is where, again, just like in chapter 16 and 17, all the topics come together. It is beautiful and magical. And these are some of my favorite demos of the year. Unfortunately, got to work with what we got. So do your best, okay? Please don't be tempted to just skate by, because even though the College Board has not made any formal announcements yet, I feel like there will be an administration of the exam at some point in time. Whether or not it's still required in the same way that it always is, who knows, right? But we are so close to the end, and, don't poop out now, right? Okay, anyway, that's all. Back to our galvanic demos. So, first of all, it says start the galvanic demo on Power School. This is that video right now, blah, blah, blah. All right, so we'll use this table as necessary. So first it says we're going to draw the setup for the cell as shown in the video. So let's go ahead and look at that cell real quick. So here is that cell, okay? And we'll see that there are two half cells. And in the land of clues that tell you what's happening, there's not a power source. Instead, there's me creepily holding that voltmeter in the back, right? Yep. See, there's a voltage running, 1.54-ish volts are running through that cell, which means that that's the clue to you that this is a galvanic cell. This is something that produces power as opposed to consuming power to run, okay? So let's go ahead and go back to our questions and draw our cell as best we can. So we have two half cells connected by that piece of paper towel in the middle. What's that piece of paper towel, by the way? Right, that is our salt bridge. So let's go ahead and draw this. All right, let's see. You do you. Here's one half cell. Here's another half cell. Let's go ahead and make this one. Oh, fancy, I know, right? So this is clearly our CuCl2 half cell with a copper electrode. And over here we had a magnesium electrode submerged in some, I don't know. Clearly it's not green, but this is our MgCl2 aqueous. This is also aqueous, right? And then in terms of what else there was, we have our we have our voltmeter, right? We also had our very, very simple salt bridge. And if we look, right, it says our half cell contains 1 molar copper chloride. So we have 1 molar CuCl2 and our copper electrode. And here we have our 1 molar MgCl2 and our magnesium electrode. The salt bridge contains sodium phosphate. And, all right, so that's our cell as doodled. So here, now it says we're going to pause and calculate the E0 value for the cell. Do your best and then continue the video. So what you're going to do now is you're going to push pause. You're going to ponder the implications of all these half reactions up here in light of the fact that this is a galvanic cell, and see what you come up with. And when you've done your very best effort, push play again, and we'll talk about the solution. Okay, welcome back. So now that you've done your, pondering, let's put it together, right? So what must E0 be? Right, so first of all, we know it's got to be positive, right? Because I told you it's a galvanic cell. 2, right, even if I hadn't told you that, there was that voltmeter that told you there was a positive voltage reading, which is your other clue that it's a galvanic cell versus a voltaic cell, right? Which would mean that it requires the input of power to do what it does, okay? So that means overall we are looking for a positive E0 value for my cell. So Next, we're going to look at my table of half reactions. Again, these are all reduction potentials, right? Meaning that the electron is always on the reactant side, okay? So we're going to take a look at this and see which one is our plausible reduction, right? For me, it's always easiest to start with my plausible reduction, which means evaluating which species I have, right? So first of all, do I even have aqueous sodium ions available for my reduction process? No, I don't, right? Because the only sodium ions are here in my salt bridge, and that's not part of my reaction, right? So that's not going to happen. Do I have some aqueous magnesium ions? Yes, I have 1 molar concentration of that, so that's a possible, right? Do I have water? Yes, I do. Do I have a significant amount of H plus ions? No, I don't, right? Which is key, though, because sometimes it'll say a solution of copper chloride that has been acidified, right? Which means that it's copper chloride, but there's also significant concentration of H plus. Nowhere does our blurb say that, right? So that's not going to be something that's there. Do we have copper ions? Yep. Do we have Cl2 gas? Nope. What about oxygen gas? All right, so yes, right? We always have oxygen gas readily available, right? It's not hugely abundant compared to other things, but it is present and it is everywhere, so it's not something that we could cross out off the bat. So now we're going to go ahead and consider which of these is the most likely one given our current scenario. Which ones might we narrow it down to? Right, we might narrow it down to these, right, because if we're talking about 1 molar concentrations, that is our standard concentration, first of all, and that means it's relatively abundant, right? More abundant than, say, oxygen gas, right? And then if we were to compare our other one, water, so obviously water is also abundant, right? But if we look at our options, right, so even if we keep that one in play, this one's negative, this one's negative, this one is actually positive, right? This one is positive as written, which means that that seems like the best bet to go with, right? And so that's what I would start with. So I would say that my reduction reaction is probably Cu2 plus 2 electrons gives us copper solid, right? And that's 0.34, right, as my voltage. Now, if I want to find my other reaction, how are we going to read this table? Right, we're going to read this table backwards, right? Meaning that we are going to go in the opposite direction. So, do we have solid sodium? No. Do we have solid magnesium? Yep, that's an option. You know what? I think that would be easier. Why don't I go ahead and erase this stuff all over my table? And now we're just going to read our table backwards, right? So, do we have solid sodium? No, so not an option. Do we have solid magnesium? Yes. Do we have H2 gas or an abundance of hydroxide ion? No. Do we have H2 gas? No. Do we have solid copper? Yes. Do we have chloride ions? No. Yes, we do, right? We have that. And do we have water? Yes. All right. So now we've looked at that, right? And we are, again, reading our reactions in the opposite direction, right? So what one other thing should we bear in mind? Right. Means that this becomes plus, this becomes minus, 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 yes? Which means that now it should be crystal clear, right, that this is the most likely option, yes? So then we would go ahead and for my oxidation, we would have our magnesium solid, gives us 2 electrons, plus magnesium 2 plus, with a value of plus 2.38. And then if I wanted to get my full reaction, right, we would then first, we would have to make sure our electrons are balanced, right, which they are actually, right? So then my overall reaction is going to be Cu2 plus Mg solid gives us Cu solid plus Mg2 plus, right? And the overall voltage is going to be the sum of those things, which would be 2.72 volts, okay? Does that make sense? Which means that copper is being reduced, magnesium is being oxidized, and that's our overall, this is our net reaction that occurs. Yes? Good? All right, and this is my overall voltage. Now, does that match the voltage that we read? No, because I think this was like 1.5, maybe 1.55, right, if we round up. Which is definitely not this, right? Which partly because I was bootlegging the solutions because I was in a hurry doing them all in one day so I could get this cool video and make it all happen. So one, the concentrations might not be exactly 1 molar for each beaker, right? In addition, due to the wires and the other equipment that I'm using, oftentimes we don't get the maximum voltage that we ought to get, right? But nonetheless, there was a positive voltage, right? Which does mean that electrons are flowing, yes? All right, so we've got our E naught value and our overall reaction. Let's see what comes next. So it says pause and label the anode and the cathode, draw the flow of electrons, and indicate the movement of ions in the salt bridge. So there are 1, 2, 3 different tasks there. Go ahead and push pause and you label your cell and we will reconvene momentarily. All right, so let's go ahead and do our labels. Anode, what is the anode? Right, the anode is the place where oxidation occurs, right? So oxidation is this magnesium one, right? So this whole half cell, right, is technically called the anode, right? More specifically, we often go ahead and label the electrode as the anode, right? So the site of our oxidation is there, right? And so this whole half cell would be called our cathode, right? If we were just labeling one part, it would be this part is called our cathode, right? The place where reduction occurs, okay? What else did we have to label? The flow of electrons. So if this is my anode where oxidation occurs, oxidation being the place where we produce electrons, right? That means electrons are produced here, which then means it makes sense that they flow here, through here, so that way then they can be used for that reduction step that happens there. Yes, does that make sense, right? So wherever we make the electrons, then they flow through to the other side where they can do that reduction step. Finally, we would like to indicate the movement of ions in the salt bridge, okay? So if we're going from magnesium to Mg2 plus over here, right? So we are making Mg2 plus, yes? That's what's happening, right? Making Mg2 plus. If I'm making cations, what needs to go in that direction to maintain charge neutrality? Right, we need to go ahead and have our phosphate ions migrate in that direction, yes? We need anions to go there to balance charge with all those newly produced cations, right? Whereas in the copper side, we are going from copper plus to copper solid, which means that we are consuming my cations, so then it makes sense that my cations are going to go over there, yes? All right, last up, we are going to do 2 very quick and simple follow-up experiments. Solid magnesium is added to the aqueous copper, and solid copper is added to aqueous magnesium chloride. So go ahead and write balanced reactions for these, and then we're supposed to predict if both will occur. All right, so I think we can write those reactions really quickly, right? So we have solid magnesium is added to our aqueous copper 2 chloride, and obviously this is a single displacement to produce this and some Cu solid, right? Alternatively, we are also taking our solid copper and adding that to our aqueous magnesium chloride to produce CuCl2 and magnesium metal. All right, so then I ask you, right, to write balanced equations, and then I ask you, will they occur? Or in other words, will both reactions produce product? And then to explain. So you take a moment, pause, ponder in light of all the things we've just looked at and talked about, and see what you think. And then obviously come back for the answer. Okay, so what did you decide? Oh, well, actually, you know what? Let's predict and then discuss, right? So if we look at the net ionics here, right? So this says Mg solid, right? If we're looking at the net ionics, right? Cu2 plus is going to give us Mg aqueous, right? Plus Cu solid, right? This one says Cu solid plus Mg2 plus is going to give us some Cu2 plus Mg solid. Now, think about that in light of what we just said here. Right, that cell only gives us a positive voltage set up like this, yes? Let's say that one more time. This cell only gives us a positive voltage if we set it up like this, okay? Which means that if we go back and look at my reactions, only the one that's written that way is going to be spontaneous, yes? It's the only one that's going to happen on its own without outside energy put in, right? So Cu2 plus Mg solid. Cu2 plus Mg solid. This reaction will occur as written. This one will not. This one will require the input of approximately 2.72 volts, right? Because it's the opposite. This one will require the input of 2.72 volts in order to occur. Yes? Does that make sense? That's what the meaning is of something having a positive E naught value versus a negative E naught value. Yes? So if we could set this up, we could put copper in some aqueous magnesium, but nothing's going to happen without the input of some energy. If we input some energy, yeah, absolutely, we can get our aqueous copper and our solid magnesium. But otherwise, nothing is what we'll observe. And oh my gosh, let's go check it out and be sure that we agree. So it's slowly playing, very slowly while I do my creepy thing. We can fast forward just a little bit. I had to do this 2 times because the first time I did it, I accidentally knocked over one of the buckets with my creepy calculator moving. Super annoying. Then I had to go set it up all over again. Super annoyed. And so, here we're going to take that piece of magnesium and we're going to drop it into that copper chloride, and you will note, oh my gosh, it is definitely reacting. And here is where we want to be careful and conscientious, because our initial feeling might be like, oh geez, look at all those bubbles. It's definitely producing a gas, right? Because that's definitely what it looks like. But then we might want to do some follow-up tests, right? Because if we look at our balanced reaction, there's definitely no gas produced in my balanced reaction. And I really should have been wearing gloves. Yep, I should be wearing gloves, right? But you'll see, right, that we're definitely getting the formation of solid copper. And you'll see here, right, it's not so much gas as that reaction is so exothermic that we are basically boiling off the water that's in contact with the metal, right? That's in contact with where the reaction is occurring. Whereas if we take a look at that copper that's sitting in the magnesium chloride, oh look, nothing is happening, right? Which makes sense in light of what we just talked about, right? The reaction of the solid copper is going to require the input of energy to happen, whereas if we let that magnesium sit in that copper chloride solution, right, the reaction would go until completion, basically, right? All right. Thank you for listening to our, altered version of a demo and discussion day. Make sure you have very good notes. Any questions that you've jotted down, go ahead and ask them in that Chapter 20 discussion block, or you can use any of those other methods. All right. Thank you for listening. Be good, and I will see you soon. Bye.